We have a converging lens up on the board here right now. We know that in order to find the image that's produced as a result of a certain object, a certain distance away from this lens, we have to draw two rays. Two rays. There's millions of rays of light reflecting off of this object. We need to draw two of them, the two that are very predictable. The first ray that we're going to draw is that ray that reflects off of the top of the object and goes parallel to the principal axis. Where does that go? Where does it refract? This is really what we're talking about, right, is refraction. Light bends when it goes through this lens because the lens is a different material, causes a change in speed. Where does it refract, Simon? Good. Refracts down through the focal point, right down through there. Keeps going forever and ever and ever. Second ray goes from the top of the object where? Devin, from the top of the object where? Good. Down through the middle, down through what we call the optical center. And where does it go from there? Bailey, where does it go after it goes to the optical center? Yeah, it just keeps going straight through, just like this. Okay, we got an image that's formed over here, where the rays intersect is the top of the image. There's three characteristics of this image. What are they? What's one of them? I don't care what order you give them to me either. Maria? It's inverted. Another characteristic. Tom? It's larger. It's inverted because we can clearly see that it's upside down relative to the object. We can see that it's larger than the object. And finally, the third characteristic, this is the harder one. Well, at least this was the harder one. Now it may not be so hard. Oh, it's a real object, which means that it can be projected onto a screen. Sorry, a real image, I should say, which means that it can be projected onto a screen. We put a white screen right there or some kind of piece of paper or whatever. We can literally see an image of that object projected onto that piece of paper. We can project it onto a screen. Now, Bo, how do we know that that could be projected onto a screen? Good. Solid lines intersect. Good. Let me draw another one. This time we got our object that's really, really close to the lens. This is like a magnifying glass, right? When we have our object within the focal length. If the focal length is 10 centimeters, maybe the object is 6 centimeters away from the lens. First ray? First ray is going to reflect off at the top of the object. Daniel, where? Oh, parallel. Okay, parallel. And then where's it going to go from there? Good, through the focal point. Good. Second ray is going to go where? Brian, where's the second ray going to go? Good. To the optical center of the lens, goes right down through there. Those don't intersect on the right-hand side. In fact, they spread apart, right? They go away from each other. So what do we do with that? Maddie, what do we do with that? Yeah, let's extend them back as dotted lines. Now, there's no real official rule that you have to make those dotted lines. That's kind of my thing, right? I talk about a real image being formed whenever you see solid lines intersecting, a virtual image being formed whenever you see dotted lines intersecting. That's why I make these dotted lines, so that we can tell that it's a virtual image that's produced when they intersect. So one of the characteristics is that it's virtual. Dotted lines intersect. Two other characteristics. What's one of them, Emma? Good, it's larger. Quite a bit larger. Looks like more than twice as big in this case. Although how much larger it is depends upon exactly where in there the object or the object is placed. Okay, what's the third characteristic? The one that we haven't given yet, Caitlin? Yeah, it's upright. It's right side up. Good. That's a convex lens, a converging lens. The next kind of lens we saw was a diverging lens. What's the other name for a diverging lens? Concave, caved in the middle, thinner in the middle than it is at the edges. Diverging, why? What's the reason the name diverging comes about? Yeah, rays that are parallel to the principal axis. All rays diverge here. So rays that are parallel to the principal axis diverge or spread apart from the focal point. All right, we got an object that's way out here, way beyond the focal length. In fact, it's beyond twice the focal length here. First ray is going to go off the top of the object parallel to the principal axis. Where does it go from there? Daniel, where does it go from there? Up to the right? Yeah, it goes up to the right, diverging away from this focal length. from this focal point right here. In other words, if I had a ruler that went through this point right here and through this point right here, then it would follow that line. Okay? So it goes up and to the right, away from the focal point. It diverges away from the focal point. Second ray bow goes where? Yeah, to the middle. And where does it go after it goes to the middle? To the optical center? Yeah, it keeps going straight through. Good. Do those intersect? Yeah. I mean, it's not showing that they're intersecting yet, but we can make them intersect. Really? Yep. Now, a little bit later on, we're going to talk about curved mirrors. You got to be careful about that because mirrors, of course, are going to reflect light. The diagrams are similar, but we can't go with entirely the same reasoning, entirely the same lines, because again, they reflect light as opposed to refract. So you're not going to be able to make it go straight through there. But in all lenses, convex or concave, that second line will go straight through the optical center every single time. All right, let's extend these back. They don't intersect here yet. Let's make them intersect. Let's extend this one backwards. Let's extend this one backwards. We find that they intersect right there. The characteristics of this image. Tom, what's one of them? It's virtual. I don't know why I always want to list that one third. It doesn't matter. We could list it first. Okay. What's another characteristic? Maria? It's smaller. Yeah, it's quite a bit smaller. And the final characteristic? Maddie, what's the final characteristic? It's upright. Now, I'm not going to draw another ray diagram for the concave lens or the diverging lens, because in the end, all 5 of these diagrams end up being not exactly the same. That's not right. They're not exactly the same, because the size and position of this image does change a little bit depending upon where the object is, but the characteristics will all be the same. In all 5 cases, the image will be smaller than the object. It'll be upright, and it'll be virtual, right? Yesterday, for you guys in period 1, we introduced 2 equations that can describe what we've just done graphically. The 2 equations are, 1, the thin lens equation. 1 over f is equal to 1 over do plus 1 over di. What did f stand for? The focal length. Good. And what units would focal length be measured in, Tom? Centimeters, meters, miles, light years, although I don't think I've ever seen a problem where the distance was measured in light years, but it could be, I suppose. As long as you're consistent for f, do, and di, it doesn't really matter what units you use. The standard units are meters, right? Go with meters if you're confused about that. Go with meters because it always works. But in this case, centimeters often ends up being the more convenient unit. And since we've got centimeters in each term, the units end up canceling out. It doesn't really matter what we use. DO stands for the object distance, the distance from the lens to the object, and DI stands for the image distance, the distance from the lens to the image. The other equation is the magnification equation. M is equal to HI over HO equals negative DI over DO. This little negative, it's on your data sheet, so you don't need to worry about forgetting it unless you don't check your data sheet. It's important. You might think that negative doesn't make much of a difference. It does. Okay, it does, and you're going to see why in a little while that negative is especially important. It's in there to make everything work. Okay, it's been put in there for the sole reason of maintaining the sign conventions for all those variables that we learned yesterday. Let's take a quick peek at those sign conventions. They can all be either positive or negative depending upon the scenario here. Let's look at the first 3 variables, f, do, and di. The focal point, or the focal length, I should say, the object distance and the image distance. What do all 3 of these have in common in terms of when they're positive and negative? Yep. Good. They're positive if they're real, and they're negative if they're virtual. So if you have a real focal point, then the focal length is positive. If you have a real object, then the object distance is positive. If you have a real image, then the image distance is positive. When do you have a real focal point? We drew 3 ray diagrams up on the board the last couple minutes here. In 2 of those ray diagrams, we had a real focal point. In one of those ray diagrams, we had a virtual focal point. Which ones did we have a real focal point for? Think about what that might mean, a real focal point. When do you have a real focal point? When is a focal point real as opposed to not real? There, but not real. Yeah, when you have a converging lens, rays of light really converge at the focal point. Okay, that's going to be a real focal point. In other words, when you have a converging lens or you have a convex lens, you have a real focal point. You have a virtual focal point or a negative focal point when you have a diverging lens or a concave lens. The object distance is real, or the object distance is positive when you have a real object. For you guys in Physics 30, that will be always. So you never have to worry about DO being a negative value in Physics 30. If you take a physics course in university and you do lenses, you may have to worry about DO being negative. It's not crazy hard, but the only time that that would ever appear is if you have a system of 2 lenses, okay, 2 lenses. And then you got an image from the first lens forming an object for the second lens. In certain scenarios there, the object distance can be negative. Okay, that's not going to happen for you guys in Physics 30, but again, it can happen in the real world, just not in Physics 30, that's all. Real image, well, real image can be formed whenever, right? Okay, real image can be formed. You've got to draw the ray diagram, you've got to at least think about, visualize the ray diagram to determine when DI is positive and when it's negative. Next 2 variables, we had HI and HO. What did HI stand for? Yep. The height of the image, usually measured in centimeters, but can be whatever, as long as you're consistent. HO is the height of the object. What's the pattern for HI and HO, whether they're positive or negative or not? Both? Good. So we're going to say HI is positive when it's upright image, and HO is positive when it's an upright object. And of course, they're both negative when they're inverted. You got to look at the situation. Okay, look at the ray diagram to determine whether it's going to be right side up or upside down, and then make your decision as to whether HI is positive or HO is negative, and so on. All right. The final variable that we had was the magnification, M. A lot of people will look at the number for magnification, say it's 0.5. They'll look at it and say, oh, 0.5, that means it's flipped upside down because it's a number. For whatever reason, we look at a number that's like a half or 0.5 or 0.75 and say, oh, it's flipped over. No. M is positive when it's on the same side of the principal axis as the image is, or as the object is. M is negative when it's flipped over. The amount or the value of the magnification has nothing to do whether it's right side up or upside down. The sign of it has to do whether it's right side up or upside down. The value of it determines whether it's bigger or smaller. A number that's smaller than 1 means that the image is smaller than the object. A number that's bigger than 1 means it's bigger than the object. So we're going to say M is positive when the image and object are on the same side of the principal axis. In other words, they're both right side up, M is positive. They're both upside down, M is positive. One of them is upside down, one of them is right side up, M is going to be a negative value. So it's almost the same as HI and HO, almost, but not quite. Okay, M is a relative value. So it's dependent upon HI and HO, whereas HI and HO are positive and negative based on what that particular value is. All right? All right, we're ready to do a problem here. We're ready to do a problem. Now, Got everything down pat, right? Just a matter of plugging numbers into a couple equations, solving, right? Yeah, it is. Except that you might run into a little bit of a problem solving these equations because we're dealing with these fractions, especially the first one, where you're adding fractions. How many people here feel confident adding fractions? It's been a while probably. Hey, when did you learn that? Grade 7? It's been a while since you've added fractions. We'll briefly talk about how to add fractions, but then we'll give you a nice little shortcut on your calculator just in case you're having a little bit of trouble with that, okay? Page 681. We got a 2.5 centimeter high object placed 10 centimeters from a diverging lens. First thing that I would do when I read this question is circle that, diverging lens. Okay, what does diverging mean? What is that telling us right away? Tells us that we got a negative focal point or a negative focal length. Whenever I see that word diverging, I want to draw attention to that because odds are, if I don't, when I go to do the math, I'm going to make that f, that 5.0 centimeters, I'm going to make it a positive value. I don't want to do that. That's going to give me the wrong answer. I need to make it negative because it's a diverging lens. If it was a converging lens, I'd leave it positive. What's the image distance, the image height, and the attributes? The attributes are just the characteristics that we've talked about. Using the thin lens equation, verify your answer with a ray diagram. We won't bother with that because we've already drawn all the possible ray diagrams. Okay, we'll just solve it mathematically here. 2.5 centimeters, what does that correspond to? A 2.5 centimeter high object. Oh. Nope, not the object distance. Close. Nope. Not DO, not DI. The height of what? Good, HO. HO is 2.5 centimeters. We're going to make this positive, even though it doesn't say whether it's right side up or upside down. It's safe to assume that it's right side up if it doesn't say otherwise. So we're going to make it positive. Let's place 10 centimeters from a diverging lens. What is this? Oh, what is this one? Good, DO. And DO is always positive, so we never have to worry about putting a negative on there. We got a focal length of 5 centimeters here. I'm actually going to write that as -5. Write that down there as -5 because I was reminded by that little note that I made when I read the question that f is a negative value because it's a diverging lens. We want to find the image distance, the image height, and then we want to find the attributes or the characteristics. Is it bigger, smaller, same size? Is it virtual or real? And so on. We have at our disposal for this question 2 equations. What do you want to try? The nice thing about these questions is a lot of times I ask you when we're solving a question, like, give me something. Give me something that's valid. Well, in these questions, there's really only 2 equations that's valid. Right? So try one of them. I don't care which one you try first. Try whichever one you think might work. If it doesn't, all right, try the other one. Let's try, since we have the focal length here, let's try the equation with focal length in it. Okay, if you wanted to try the other one first, that's okay. Not the end of the world. All right, so we got 1 over -5 equals, the object distance is 10 centimeters, positive 10. The image distance, all right, good. We're looking for the image distance. This is going to work. All right, you people that are good at fractions might say the common denominator here is 10. So we get -2 over 10 equals 1 over 10 plus 1 over di. 1 over 10 comes over by subtracting. It becomes -3 over 10, or di would be equal to -3.33. Those of you who don't understand what I just said, or just don't like adding and subtracting fractions, try this. Everybody try this on your calculator, please. -5 x to the -1. take the 1 over 10 over by subtracting. So let's subtract 10 x to the minus 1. Negative 0.3. Well, I just solved for 1 over di, not di. So let's say x to the minus 1 of negative 0.3, and I end up getting negative 3.333. Sorry. Does that make sense? See what I've done there? Take a look at the keystrokes there. Negative 5, x to the minus 1. That means 1 over negative 5. Then I subtracted 1 over 10, or 10 x to the minus 1. Right? This has to go over by subtracting. That gave me negative 0.3, which was 1 over di. Then I had to flip that over to get di, so I went x to the minus 1, negative 3.3 centimeters. So now I need hi. Let's try m is equal to hi over ho equals negative di over do for this one. 3 parts to this equation. You only need to use 2 parts, obviously. Probably these 2 parts right there. Hi over 2.5 equals negative di over do, 10 centimeters. Is that right? Bo? Good. He caught it. Bo's the smart one there today. It's negative 3.3, right? It's negative di. We can't just drop a negative. It's negative di, and di was negative 3.3. So that actually, as Bo said, becomes positive, right? Negative is a positive value. So what do we got there? Negative 3.33. We end up with 0.33. Multiply that by 2.5, and we get a value of 0.83. So hi is 0.83 centimeters. Okay, what about the attributes now? There's 3 of them. Can anybody give me one of the attributes? I don't care which one. Give me one of the attributes, one of the characteristics. One of them staring me right in the face. Yep. It is virtual. How do you know? Okay. Caitlin, good point. It's virtual because it's diverging lens. Be careful with that, but you're right. Okay? All the ray diagrams for diverging lenses, every single one of them produced a virtual image. So if it's a diverging lens, then it will produce a virtual image. You're absolutely right, every single time. But just be careful, because that's not the only time it will produce a virtual image. You can also produce a virtual image in one case with a converging lens. Okay, so because it's diverging, it is virtual, but it doesn't go the other way around. Because it's virtual, it doesn't make it diverging. Okay, what's the other way that we can determine that that's a virtual image? Besides what Caitlin said, which is absolutely correct. Look at this, di is negative. Let's go back to our sign conventions here. If di is negative, what do we say it was? A virtual image. So we know it's a virtual image because di ended up being a negative value. Good. I didn't actually think that was the easiest one. Caitlin got that first, but I thought that was one of the harder ones to determine characteristics. The one that's staring me right in the face, Simon? How do you know it's upright? Okay, good. That's actually not the one that I was noticing right away again, but that's correct. If hi is positive, it is upright. Good. The one that I noticed right away was that hi is 0.83, ho is 2.5. The image height is quite a bit smaller than the object, right? 0.83 compared to 2.5 is smaller. I see the two numbers beside each other. I know that the image is going to be smaller than the object. Now, if we went back to our array diagrams, okay, we draw this out, you're going to find the exact same characteristics. You guys have already drawn that on the template that I gave you a couple days ago, right? Have a look at a few questions on the board here right now. Questions 1 to 3 on 681.